So up to this point, we haven't really been too concerned with domains of logs because we haven't had any logs, but domain is always a concern of ours when we're talking about a function. We don't really want to talk about the derivatives on a graph where the graph doesn't even exist. That'd be silly, right? How fast is the graph changing over there where it doesn't exist? Funny, funny. So up to now, we've been looking for things that restrict the domain that mainly gave us division by 0, right? Variables in the denominator. What values give us 0? Cast them out. And negatives under a square root, fourth root, or even root. We want to avoid negative numbers. But there's another concern that we have now that's not a piecewise function, but a log function. We can only take logs of what types of numbers? Positive numbers. So if you ever have a variable in your what you meant? What do we call that? Argument. If you ever have a variable in your argument, you need to find the values of that variable that will assure that you have positive numbers upon taking the log of them. That's how you can find your domain. So that's what we're doing on part G. So in general, you take your argument, in this case, x squared minus 3x plus 2, and you say that it has to be greater than 0, strictly greater than 0. For a radicand, you would say it's greater than or equal to 0 if it's a square root or a fourth root. But for here, we say it's strictly greater than 0. Can't take the log of 0. Now we've set up a quadratic inequality, which they started learning about yesterday in Algebra 2. And we spent a lot of time early in pre-cal going over this as well. What types of inequalities can we solve entirely by using algebraic methods, exclusively by algebraic methods? Linear. Remember that? You can only solve linear inequalities algebraically. But even then, you have to remember to not to forget that one little caveat to the rule, right, of algebra. When you multiply or divide by a negative, you must remember to flip the inequality. Okay, so it works, but there's a catch. Now, it doesn't work for the other functions. You have to solve them some other method. You either use test values and you test intervals, or you solve it the easier way, which is by graphing it. Yeah. So let's go ahead and see how we're going to graph this. I know that it's going to be a parabola that opens what? Sideways? Help me out. Up, because the leading coefficient is positive. I want to know where the graph is above the x-axis. Yeah? Is that what that translates into, if I remember correctly? We want to know where the graph is greater than 0. That's going to be above the x-axis. Because we're talking about y values here, right? Y equals 0. Y equals this. For what values of x are the y values of my graph above y equals 0? Okay. It would be helpful to know the y-intercepts then of my parabola. X-intercepts. And to find x-intercepts, we can either guess and check. C is not going to be an x-intercept. We can use the old quadratic formula. We can complete the square and put it into a standard transformation form, or we can just attempt to do what first? Factor it. Yeah, now you can factor it with the inequality there. This factors nicely into x minus 2, x minus 1. And you can still say that their product is still greater than 0. Nothing wrong with that. Guess where it breaks down, though? The zero product property that you can use for equations doesn't work so well when you have inequalities. And this is what students try to do. And if you split that up and say they're both greater than 0, life is going to be hard for you. Okay? What do we do instead? We graph it. We use the fact that it's factored to get our x-intercepts, which are, of course, at x equals 1 and 2. And since we know those are the intercepts, we know now the parabola opens up. We also know the x-coordinate of the vertex now is at what? 1.5, right? It's always at the midpoint of the x-intercepts. Not that that's important here, but that would be where the derivative is equal to 0, and we could verify that with calculus, but we won't. We want to know where it's greater than 0. So it's greater than 0 here and here. Now remember, we're looking for the values of x. So if you recall then from pre-cal / algebra 2, for parabolas, it's either going to be everything between the x-intercepts or everything outside the x-intercepts. In this case, it's everything strictly outside the x-intercepts. And we don't want to include the x-intercepts because we want it to be strictly greater than 0. So for any value of x less than 1 or any value of x greater than 2, we're going to get positive numbers under the radical. So the domain of G is going to be the set of all x such that x is less than 1 or x is greater than 2. And that's how you would write it using set builder notation. Anybody a fan of interval notation in here? Probably those Lakers fans, huh? You probably interval. Yeah. What would that be in interval notation? Negative infinity to 1, union, 2 to infinity, right? And they all get parentheses, yeah? So either one of those works. Sweet. Okay, moving on. Part B. What's the limit as x goes to 1 from the right-hand side? From the right-hand side. Well, I guess we can use direct substitution, right? Never not first. The limit as x goes to 1 from the right-hand side. I'm going to go ahead and put the actual function here. Log of x squared minus 3x plus 2. And never not first, we'll plug in so that it gives us log of 1 minus 3 plus 2, which is log base 10, right, of 0. And that's a numeric answer, so we can box it and walk away, right? That's not a numeric answer, right? Because what is that equal to? It's equal to DNE. If you ever take the log of 0, if you're ever finding yourself taking the log of 0, you are evaluating the log at its vertical asymptote, which is nice to know, right? If you ever take the log of a number and you get 0, you're taking the log at the vertical asymptote. So if this were a free response and you realize that, you can answer the question then safely by putting DNE. Because you know you're at your vertical asymptote, though, you know that the preferred answer, especially because it's a one-sided limit, is going to be either plus or minus infinity. Now, how do you decide which one it is? If it exists at all? Remember, log functions can only exist perhaps on one side of the vertical asymptote. So maybe it's not even plus or minus infinity. How can we determine what's going on just to the right of 1? Plug in a number just bigger than 1, right? That's what we've done in the past, like 1.1. So let's plug in a 1.1. We get 1.1 squared. I'm out. I'm out already. I'm out. I'm not going to do it that way. No. No way. Is there another way to do that? Let's think of this. This is what our argument is, right? If I plug in 1.1, I'm going to be just outside the domain, right? I'm going to be just outside the domain. So I'm going to be on the side of the vertical asymptote coming in that where the graph exists or where the graph doesn't exist. I'm going to be on the side where the graph doesn't exist. So guess what the answer has to be? DNE, because I'm on the side of the graph where there is no graph. So it's DNE because no graph exists. Now, let's augment that and look at what's happening now as I approach 1 from the left. You plug in, you get 0. Of course, DNE is another safe answer. But if I plug in a number from the left of 1, now I'm on the piece of the graph where it does exist. Now it's going to be forced up or down to positive or negative infinity. So how can I tell now if it's going to be positive or negative infinity? Well, yeah, if I choose a number to the left of 1, I know I'm going to have a very, very, very small positive value in my argument, right? Yes, there you go. That's how you want to do it. If you take the log of a very small positive x value, which this graph tells me of the parabola, if I choose a number just to the left of 1, it's going to be really close to 0, but positive. As Rapp said, if you look at a log growth function, right, it's base 10. That's kind of important. So if it's a log that's a growth function, then remember, if you take the log of any number less than 1, it's going to be what? Negative or positive? It'll be negative, right? And so I'm going to have a number that is negative, and it should be what type of infinity then? Negative infinity. Wow, that's some nice analysis. There you go. If it had been logarithmic decay and not logarithmic growth, then if I take a log of a really small positive y value, or sorry, a really small positive x value, and it's logarithmic decay, now anything that's less than 1 is going to be a positive number. And because it's really, really small, again, that's why it's infinity, because we're way up there. So that's how you can kind of get the sign of the infinity for these composite functions that involve logs. Pretty nifty. So both of these limits fail to exist, correct? They're both D and E technically, but for very different reasons. Very different reasons. All right, questions on that? Letter C. The limit as x goes to negative infinity. Go ahead and try it on your own. Or do it on your own, I should say. I don't want to belittle y'all's ability. Don't be in doubt either. Are you in doubt? Are you in doubt?
Definitely not.
Definitely not. That's 100% confident D&E.
100%.
Okay. 110% confident D&E. Unless you're wrong. Nice. It's a definite maybe then. I like that answer better. Good. Uh-huh. Okay, now you just got to evaluate that. You should try to use correct notation, but again, a question like this, you're not necessarily going to be graded on the notation if you just come up with the right answer. See, like that's poor notation on that middle line, right? Right, you didn't put the limit in front as x goes to that. But it's the right answer, and it's the preferred right answer. So all can be forgiven, right? The end justifies the means, but you just might lose a few points along the way. And friends. Yes, más mejor que bueno. Yes, good. And I'd prefer that, where you actually you don't show any intermediate work, so there's no risk of showing poor notation. You just go, boom, right to the answer. Yeah. Well, then if you do this, then that would not be infinity, so that would be what? X, right? X. Yeah, again, poor notation, but executed at the end well. Okay. As long as you execute. Yeah. There you go. See, that's good notation, proper notation. Yes. Are you there yet?
I think so.
Yeah. I believe so. Yeah. They're kind of far away from the other one, right? That's wow, way on the other side. All right, this is composition. So let's just kind of do it without any notation. You could bring the log to the inside, of course, and take the limit as x goes to negative infinity of x squared minus who cares, right? We have two ways to evaluate the x squared minus who cares. You can think of the x squared dominating the growth of the other terms that are smaller by degree, so you can just plug in a negative huge number into the leading term. Negative huge squared is positive huge. So this goes to positive infinity. Or you can just think of the graph of a parabola that opens up and realize as you go out to both sides, you're going up to infinity. Now here's the notation that I saw some people write. And again, this would be the wrong notation for a formal presentation. But for you, if you're doing like multiple choice, we all know that we're not actually trying to take the log of infinity, because infinity, in fact, is not a number. But in essence, we know what that means. That means we're taking the limit as x goes to infinity of the log function. That's really what we're doing. Okay? And of course, then what happens to a logarithmic growth? Because what's the implied base? 10. A logarithmic growth function, as x gets really, really big, the answer is it does go to infinity. And of course, infinity is technically non-existent, so D and E would be a correct answer, but not as informative as infinity. Good. All right. Properties of logs. The things that make logs so useful are their properties, but that's what also makes logs so undesirable for some students, not y'all, but some. They have an aversion to logs. Remember, logs are just the rules of exponents turned on their head, because logs and exponents are inverses. So we'll look at the property of logs real quickly and relate them to the exponential properties. The first one says the log of a product is not the product of the logs, but rather the sum of the logs, yeah? What logs do is they take everything down one rung on the operational ladder. Your dear Aunt Sally's ladder. Not a very tall ladder. I wouldn't use it to hang Christmas lights, but it's a ladder nonetheless. On the top rung, you have exponentiation. I guess you have parentheses above that. But for logs, you have exponentiation. A log will turn an exponentiation into one rung lower, which is multiplication. And logs also then take multiplication and turn them into one rung lower, which would be addition/subtraction. Yeah. So that's what we're doing here. We're turning multiplication into addition. The log of a product, this is some of the logs. And it comes from the exponential rule. If you have a to the x times a to the y, and you are multiplying, what do you do with your exponents? You add them, right? And remember, the log is the exponent, so it makes sense now. A multiplicative process turns into an additive process. Same thing with division, same priority level. The log of the quotient is not the quotient of the logs, but rather the difference of the logs. Does it matter which term is negative? It's the denominator, right? The denominator. And here's the one that turns exponentiation into multiplication, which we've already seen. The log of something raised to a power r, the r will come out front, and it becomes multiplied. So what a log does is it linearizes essentially an exponential function. And if you've seen old engineering paper, they used to make engineering paper that had the lines vertically and horizontally. They got closer and closer together. You had log paper, log paper, and semi-log paper. And the semi-log paper, they do this in statistics too when you're doing linear regression analysis. But a log linearizes an exponential function. It's kind of nice. Makes it easier to work with. All right, and then the other two that we've already seen, this is the one we started off class in the warm-up. We have log base b of b to the x is x, which is the same as b to the log base b of x, because log base b and exponentiating base b are what's again? Inverses. And then here's a nice little one-to-one thing. If log base b of m equals log base b of n, then because logs are one-to-one, you know m equals n. And you can even write that as exponential. If b to the m equals b to the n, then m has to equal n, because they're both one-to-one. I called this method the GTBTS method back in pre-cal to get the bases the same method. It also works with logs. You can set the arguments equal if the bases are the same. All right, are we ready for calculus yet? No, not yet. We're solving log equations. Why do we spend so much time reviewing logs before we get to the calculus? They are fun. There you go. They're so fun that College Board's favorite toy is not the yo-yo, not the jumping rope, but the logs. What? The Rubik's Cube. That's way too advanced. All right, here we go. Log base what of x plus 1 equals 3? What's the base? 10. Anyone know the answer? 999. Did you guess that? How'd you do that? Yeah. You rewrote it in terms of an exponential. Yeah. It's very, very often the case where you convert it to an exponential function to solve the equation. So you do your little around the world thing, right? The if and only if theorem. So you get 10 to the third power equals the argument, which is x plus 1. Now you've turned it into a linear equation. And, of course, x equals 10 to the third is 1,000 minus 1 is 999. Now, you want to make sure that it works. When you convert the problem, you need to make sure it works. Plug in a 999 plus 1. Is that a positive number? Yeah. In fact, if you want to find the domain of the log equation before you start, take your argument, x plus 1, and say it has to be greater than 0. And now you know that all your solutions have to be greater than negative 1. And, of course, 999 is greater than negative 1. So it works. All right, letter B. Ooh, it's exponential. Well, we could try to get the bases the same. We have an exponential on the left. Can we write 14 pretty easily as a power of e? I don't think so. I can't do it. I can't do it. So what do we do instead? We will take the natural log of both sides. Good. And just like when we take the derivative of both sides with respect to x, the log must go in front. Because we're not multiplying both sides by log, we're applying the function, natural log, which goes in front. Now what that allows you to do with the exponent is bring it in the front. And you can think of that like that. Or there's another way to think about it a little bit quicker, but if we did think about it like that, when you bring the 3 minus x up front, would it need to be in parentheses? If you did it like this, would the 3 minus x need to be in parentheses? Yes. Now, what is the natural log of e? Oh. What is the natural log of e? 1. Thank you. It's 1. So 1 times anything is itself, so you get 3 minus x equals the natural log of 14. Of course, you could go straight from here to here, right? Using the property. Natural log of e to the blob, of course, is just the blob. And now all I have to do is solve for x. X would equal 3 minus the natural log of 14. You want to stop there? I would. You think College Board would stop there? Maybe not. They might call the natural log of 14 7 times 2. Here's where they start playing. And then you would get 3 minus. I could use the properties of logs to expand it, and I would need some kind of grouping symbol. The natural log of 7 times 2 is the same as the natural log of 7 plus the natural log of 2. But then because there was a minus sign in front, I would need to then distribute. Yeah. Something like that. Yep, okay. I don't know if they do that, but be aware of that. 7 and 2 are both primes, so not much you can do with there without getting extravagant. We don't want to get too extravagant. All right, this one. You have log of x minus 1 equals 1. What do you notice about it? It's printed in black. It's got how many logs in it? 2. Okay. So this term requires x to be greater than 0. This term requires your x to be greater than what? 1. So in order to work for both of them, our values have to be what? Greater than 0 or greater than 1? Greater than 1. Yeah. So that's like finding the domain of the equation. Just kind of interesting to think about before we start. Any value of x that we find has to be bigger than 1 in order to work in both of them. So how to proceed algebraically, systematically, algorithmically. E both sides? Okay. You can also exponentiate both sides. Yes. You can. It's the same as taking the natural log of both sides, kind of, in spirit. Now what happens to the left? Do they go away? I know that e to the natural log of blob is just a blob, but what's e to the natural log of blob plus blob? I'm not sure if I like that. Distribute the ln?
You can make it one ln of x by using that rule. It would be ln of x divided by x.
Yeah, I would not e it yet. That's not a bad thing to do. What I want to do is I want to get a single log. If I can get a single log, then I'd be happier. So notice that I have a difference of 2 logs. The properties of logs, that's them. They not only work from left to right, they work from right to left, right? To left, right? To left, right? To left. Okay, so we could say that the difference of the logs is the log of the quotient. So you pull one log out, the positive term x is in the top, the negative term's argument's in the denominator. Now that you've isolated the log, Brandon, now it would be a good time to e both sides. Now, e to the natural log of blob is the blob. And on the right side, I get e. So now I've gotten rid of the logs altogether, turned it into an algebraic equation. I would cross multiply here, x equals e to the x minus 1. If you distribute, you get x equals ex minus e. If you bring the ex to the other side, you get x minus ex equals negative e. If you factor out an x, now you get 1 minus e equals negative e. And then you divide through and you get negative e over, oops, I put 6, wow. Negative e over 1 minus e. Oh boy. Now I don't like the way that looks, so I will multiply by negative 1 over negative 1. And I get positive e over e minus 1. I like that better. Is that number greater than 1? Does it work? If we think of e as being 3-ish, then 3 over 3 minus 1 would be 3 over 2, which is bigger than 1. It should be bigger than 1. Yeah, so it works. Now, if you didn't want to e both sides, which is fine, I like e-ing both sides, exponentiating both sides, you could think of the natural log as log base e, right? And then you can just use your good old conversion formula around the world. E to the first equals that. You get the same thing. But I like the algebraic process of exponentiating both sides. They both work. So converting from log to exponential or converting from exponential back to log. Sometimes it can be helpful to put it in a different format. All right, letter D. Letter D. I got log, log, log. Now you have two options here. You can either bring all the logs to the left side and condense it down to a single log, or you could say I'm going to get a log on one side and a log on the other side. And of course, then if I can get log of the same bases on either side, I can set the arguments equal to each other. So that's what I think I'm going to do. I got log base 10 of 6 over there. Let's think about the domain very quickly. The first term requires x to be greater than 0. The second one requires x to be greater than negative 1. X plus 1 has to be greater than 0. Now, what that does, by thinking about that in the end, you're avoiding having to plug your numbers back in and test them out. Now, which one of those domains would work for both of them? Greater than 0 or greater than negative 1? Greater than 0. Everything that's greater than 0 is also greater than negative 1. So our answers have to be positive. All right, step 1, they're both log base 10, thank goodness, so we can condense it. We have the sum of two logs, yes? That's going to condense down to the log of the what? Product. So it's x times x plus 1. Now I have log base 10 of blob equaling log base 10 of blog. Did I get the bases the same? Yeah, so guess what I can do? I can now set the arguments equal to each other. Now, if you want to use that property, go ahead and do that. Or if you want, you can exponentiate both sides base what? 10. And that also works because what's 10 to the log base 10 of blob? Blob. And on the other side, what's 10 to the log base 10 of blob? Blob. So however you want to think about it, you get to this result. Now, of course, if you distribute, you get x squared plus x. You would probably subtract the 6, get it equal to 0. Notice we've turned our equation into a what type of polynomial? A quadratic. And we know the quadratic can have up to how many solutions? 2. Our original arguments were both linear. Linears can have maximum how many solutions? 1. Because we've changed it from a linear to a quadratic, this is where we need to be extra cautious and be on the lookout for what? Extraneous solutions. Yeah. I don't want to have to plug my answers back in to test them out. All I need to do is look at their ID at the end and look at their age of birth. If they were born after 0, then we'll let them in the club. All right. Let's factor this. Does it factor? I hope not, because I want to use the quadratic formula. It does? Bummer. I guess I could still use the quadratic formula, but I didn't really want to use it. Is it important to keep it equal to 0? Yeah, sure is. So now we can just go straight to the answers. X equals negative 3, x equals 2. Box them up, put a bow on it, and send it to our best friend. No? No. Send it to our worst enemy, maybe. Because you got a mole in there, right? You got an imposter. You got someone who's going to infiltrate. He's an extraneous solution. Only one of those is greater than 0. Which one? 2. Yeah, so x really only equals 2. And you don't have to plug them in to try them out because you've thought about the domain of the equation. You could certainly plug them in and try them out. If you plugged in a negative 3, you're going to discover right away it doesn't work. You plug them back into the original equation, though, right? What's the log of negative 3? Doesn't work. Negative, right? Good. All right, how much time do we got? We got about 16 minutes. Perfect. Perfect. That's just enough time to BOTC. Which, of course, you know what that means now. I don't know why I put it in parentheses. It's time to bust out the calculus. Why calculus? Well, of course, if we have a log function I know you've all been wondering this whole time, how fast is the graph changing at that moment? You all want to know. It's instantaneous rate of change, right? Okay, well, I'll show you. This is example 6. If y equals the natural log of x, solve for x, then find dy dx using implicit differentiation. So I'm giving you a clue now how to derive the derivative of the natural log of x. I didn't give you the clue when we derived the derivative for arc sine of x, right? We talked about it. Let's go ahead and solve this for x. How do I solve it for x? Do what with both sides?
Do both. Like have both sides like e raised to the y.
Right. Yeah, it's actually called exponentiate both sides. We could say e both sides if you want. I'm okay with that. That's kind of cute. We'll e both sides. Or you can use the conversion formula, right? So I got e to the yth power equals e to the natural log of x is x. But again, if you want to just say that that's log base e, you could say e to the y equals x around the world, whatever. Okay, so now it's not solved for y. No big deal.
Teacher,
I can take the derivative.
At this time, please take out the QR code that was placed in your teacher boxes and allow your seniors to vote for their prom theme. If you have mixed classes, please make sure that only seniors are casting their votes. The voting will only be open today from 11:25 to 11:40. So seniors, today will be your only time to cast your vote for your prom theme. Please begin that at this time.
All right, I'm going to tell you what, guys. I'm going to look for a QR code. Y'all finished taking the derivative implicitly, okay? And
Sorry, teacher, that is actually tomorrow.
oh, yes. Okay, that's what I thought. That's what I thought. Because okay, good. Oh, good. Good. Okay, no, I thought it was tomorrow. I knew I had to have a QR code. Tomorrow we'll vote on senior prom. There's 3 different categories that Miss Velasquez and Colton came up with. One of them was Math Party USA, right? Yeah, Under the Sea, Math Party USA, and out of money at out of spending money at the mall. That's the other thing. Yeah, out of spending money at the mall. So, yeah. All right. What do you do if you're at the mall and you're out of spending money? You just walk around. You window, right? You browse, you go to the stores. Can I help you? No, I'm just looking. I'm out of money. All right. I don't know. It could be, you can interpret it either way. It's your prom.
So that means you should go home and see your prom?
I guess. I don't know. Isn't that what happens anyway? All right. Let's take the derivative implicitly. On the left side, we have e to the blob. What's the derivative of e to the blob? E to the blob times the natural log of the base. Well, what's the natural log of e? 1. Times the derivative of the blob with respect to x. Don't forget that. And on the right side, what's the derivative of x with respect to x? dx dx, or 1. Okay, so now we'll solve for dy dx, and we get what dy dx equals 1 over e to the yth power. And there you go. What's the derivative of y equals the natural log of x? 1 over e to the yth power. Is that like a Snickers bar? Is it satisfying? Oh, yes, but what is e to the y? Thank you. That was not very satisfying. It's like being at the mall, out of money, Snicker bars machine right in front of you. You don't have enough money to eat a Snickers bar.
Pardon the interruption, teachers. Please turn your TVs to channel 4 for the morning announcements, or you can view them on your iPads at VHSTV.com.
Sounded like Brandon, didn't it? But he's supposed to be in here. Okay. Yes, e to the y is in fact x. Remember that up here? So I can substitute e to the y with x, and there you go. The derivative of the natural log of x is 1 over x. Yeah, now you got to think about the domains, because what's the domain of the natural log of x? 0 to infinity. X has to be greater than 0. What's the domain of 1 over x? Everything but 0. So the derivative of the natural log of x is only going to be the positive branch of 1 over x. Okay? Let's see if we could figure out why graphically that works. If I graph the natural log of x in blue, This is y equals the natural log of x. Let's see if I can sketch its derivative, not knowing what it is, let's say, on the same coordinate plane. As I come in from the left, right next to the vertical asymptote, my slope is a really big positive number, yes? It's super steep. So the y value is going to be a really big positive y value. Where do we find those? About right there. Really big. As I go to the right, my slopes are still positive. In fact, my slopes are positive everywhere because the function is monotonic increasing. But what are the slopes doing? Are they increasing or decreasing, the slopes? The slopes are decreasing, okay, but they're still positive. Now, as I go out to the right, my slopes are approaching what? Big number. The slopes, the y values are approaching a big number. The slopes are flattening out, approaching 0. Will the slopes ever equal 0? No, because if the slopes equaled 0 or approached 0, if they ever equaled 0, this graph would flatten out, and it never does. It does go to infinity. So my y values are decreasing, approaching 0. It must look something like that. And of course, that is the right-hand branch of 1 over x. Okay. Now, if I looked at this function, let's look at this. What transformation, we just learned this today in pre-cal, does that do to any graph if you take the absolute value of x? Yeah, it makes all your what values positive? X's, right? If you look at it, pick any input you want, make it positive, and now take the natural log of it. So if your values are already positive, x values are already positive, they don't change, right? So that would look like this. It would be the same graph. Oops, wrong one. It would be this. It would be the same graph. But now notice I can choose the negative x over here, which before I couldn't. If I choose -1, the natural log of the absolute value of -1 is the same as the natural log of +1, which is 0. And that works with every negative value of x now. I could choose a negative value of x over here, and it's going to graph it as if it were positive. So remember, this function here, by definition, will have y-axis symmetry. And the way we obtain it is you leave positive x's alone in quadrant 1 and 4, and you just reflect that across the y-axis to get the other branch. And if there was anything over here in quadrants 2 and 3 prior, it's gone now. So that's what the graph of the natural log of the absolute value of x looks like. Let's see what the derivative of that function looks like, and I'll use red again. Let's see if we can figure it out from the graph. Well, if I'm going to take the derivative of this positive branch that I did before, my argument's still going to be the same, and I'll get the same little red branch, won't I? Because it's the same graph over here in positive x land, so it's the same derivative, yeah? Let's now look at the negative branch. If I'm graphing the slopes over here, notice coming in from the left, my slopes are positive or negative on this left branch of the absolute value natural log. They're all negative, so all my y values are going to be negative, but they come in from the left, steep or not steep, Mr. Miller? Not steep. So it's going to be a very diminutive negative number. And by diminutive, I mean its magnitude. Okay? And as I go to the right, they're getting steeper and steeper. So my magnitude of my slopes are getting bigger, but still negative. Yes? And they're never going to go vertical, but they're going to approach vertical. And as I go back out to the left, they're never going to get 0. So it looks something like this. Now, is that in fact the other branch of 1 over x? Yes, it is. So, what do you think then the derivative of the natural log of the absolute value of x is? It's still 1 over x. And all we've done now is we've opened it up to negative x values. That's pretty cool, because the derivative with respect to x of the natural log of x is the same as the derivative with respect to x of the natural log of the absolute value of x, and they're both 1 over x. And that's not often where you can just drop the absolute values when you take the derivative. But it works in this case. And that's pretty nice. 6 minutes? Okay, thank you. All right. Use your result from example 6 and the chain rule. What's that? Oh, yeah, okay. I was going to use that other minute. Yeah. Okay. But Garrett wants to see. Garrett wants to see. Okay. All right. We'll stop right there for today, I guess. And we'll pick up with 7 tomorrow, I guess.